Okay, so I'm going to talk today about, I guess, what's called Bayesian mechanism design. And to get started, let me just give you a couple of examples. Just it'll give you a sense of kind of like why these problems are interesting and why there's kind of like all these algorithmic game theory people are working on this. So let's say that there's one buyer, one seller, and all the examples so far will say there's 2 items for sale, and the buyer has value vi for item I, and they have value, I'll write this more generally than we need to for 2 items, but sum I vi for set S. So their valuation is just additive or a linear function over the items. And let me just give you, one more thing, and we'll say that the buyer's value drawn so the values are going to be drawn independently for each item, and the seller's goal is to design a selling scheme that maximizes the expected revenue. Okay, so I think this will actually maybe start to be, if it's not completely clear, I think it'll start to be clear with examples. So, sorry, and also you should, just to give you motivation for the model, you should think of these distributions as kind of like representing there's a population of people, and you're a seller, you have a store. You don't know who's walking into your store, but you know that they're kind of like a random draw from this population. And you have to treat everyone in the population the same because you don't know anything about them when they come in.
Buyers have identities, so they can come back to your store?
Let's say so for this model, let's start with that the buyers, they walk in, they interact, they leave, and they don't come back after that.
And are you allowed to use probabilistic?
You're allowed to use probabilistic. So the question you asked is only relevant if you use randomization. So if you're not using randomization, like the buyer can walk in, either they leave with something or they don't leave with something, and then they can leave and they can come back. The same thing will happen when they walk back in. So there's no reason to go multiple times. If you use randomization, then there is a difference between what you can do if the buyer is allowed to buy something, see what happens, and then leave and come back, and if you can force them to never come back. But I wasn't going to get into that with this.
So you can have menus of the sort. You can buy it for $100 or pay $80, but only get it with probability 90%.
Correct. And you would say the buyer is not allowed to then pay $160 to get 2 draws from 90%. Not that they would want to, but yeah. Is that okay? So let's just do some examples. So let's say that okay, so let's just say that the first example, the buyer's value for each item is drawn independently and uniformly from the set 1, 2. And we can try and reason about what the optimal mechanism or the optimal selling scheme would be. So I'll comment that a tempting thing to try and reason is that you look at this and you say, okay, the buyer's value is linear or additive over the items. So it doesn't matter whether he gets item 1, his value for item 2 is his value for item 2. It's not like if he gets item 1, he has more value. If he doesn't get it, he has less value. And you can also look and say, okay, the buyer's values are drawn independently for each item. So like even if you condition on the value for item 1, it's not like it tells you anything about the value for item 2. And it maybe suggests you should say, okay, that right there's not really that much interaction between the items, and maybe the right thing to do is just to sell the items in isolation and let the buyer do whatever he wants. So what would that look like? It would look like setting something like, okay, let's just write this. And so it would look like you just set a price on item 1, you set a price on item 2, you tell the buyer, buy whatever you like, and that's it. So in this case, if you're going to set a price on item 1, you can set either price 1 or price 2. They both give the same expected revenue. It's 1. And ditto for price 2. And so the revenue you get from this is 2. Okay? And it turns out there's actually a better thing you can do for this example, which is to set a price on both items together at 3. So what this means is that you tell the buyer, you can pay me 3 and you can get both items, or you can pay me nothing and get nothing. And now we can just do some quick math and observe that the buyer is going to choose to purchase this as long as their value is at least 3. This happens with probability 3/4, so you get revenue 9/4. Okay, and this is better than 2. Okay, so the point is that you do, even in this super simple example, you do need to do a little bit of non-trivial reasoning. Okay, so what's the next example is that you might need to use randomization. So let's change this a little bit and now say okay, so let's say now the distributions aren't identical and the second value is drawn from uniform 1, 3. So now here we can quickly check through over all the deterministic things you can do. How much revenue do they get? So if you sell, let me just write it like this. So one thing you can do is you can set P1 equals 1, P2 equals 3, and this will give you revenue 2.5. Another thing you can do is you can set P12 equals, I think 4 is the best, and this will give you revenue, maybe you can do better. This will give you revenue 2. And something better you can do in this case actually uses randomization. So what you can do is you can offer the bidder the following 2 options. You can say either you can pay, let me process again. So you can pay 4 and get both items, or you can pay 2.5 and get 1 with probability 1 and 2 with probability 1/2. Okay, does at least the scheme make sense? So you just say you have these 2 options. You can also pay nothing and get nothing. Does this make sense? So you just tell the buyer, here's the 3 options. You can take whatever you want. And the point is that who's going to choose to do this? Well, whenever your value for item 2 is 3, you're going to want to do this, right? So this is going to give you revenue 4 times 1/2. And whenever your value is 1, but your value for item 1 is 2, then you would choose to buy the second option instead of getting nothing. So this would give you an additional, whatever 2.5 divided by 4 is. It's like so you get like 5/8. And then the observation is that 2 plus 5/8 is actually better than 2.5. Okay, so there is a randomized I'm calling these mechanisms. There is a randomized mechanism that gets you more revenue than any deterministic one, and it kind of already happens with these pretty simple examples. Okay, so let me just maybe state, without writing down the examples, because now they're getting a little bit messier, 2 other facts. I won't write it down. So we also know so we also know that if, in both of these examples, I had the values be independent. If the values are correlated, so there's just an arbitrary correlated distribution on your values for both items, then we know examples where the optimal randomized mechanism gets infinite revenue, but the optimal deterministic mechanism gets revenue 1. So there could be an infinite gap between what you can get using randomization and what you can get without it. We also know, so we also know the following. So say we're back in the item values are independent and even IID, then the following can happen. That if you start with, say, IID from the distribution D1 for each item, you get some revenue in the optimal mechanism. You come up with a new distribution, D1 plus, that stochastically dominates D1. And now you look at the optimal revenue for D1 plus by D1 plus, and the optimal revenue can go down. Okay, so even though, right, there's a coupling between the 2 markets where every bidder has higher value for both items, when you find the optimal mechanism, the revenue is lower. Okay, so these are just examples, just I guess hopefully to convince you that there's some pretty interesting things going on. That's why so many people are interested in developing tools just to understand this area.
You're also assuming that all of the buyers are going to do what's best for them.
Correct.
If one of them doesn't do what's best for them, that can end up hurting you in the end.
So if one of them doesn't do, so that's a modeling assumption, I guess, that the buyers are like selfish or self-interested. If they don't do what's best for them, I guess then that's getting more into the game theory questions of, like why would a buyer walk into a store and do something that's.
But it's possible. I mean, it's possible that your revenue could go down if a bunch of stupid people came in and did the wrong thing.
That's definitely possible. Yeah. So okay. Yeah. So I would say that I think is a good argument why in practice we don't so much see randomization everywhere. One of the reasons is, I guess, like you said, that if you asked, maybe not people in this room, but if you asked normal people to go to a grocery store and buy lotteries over food, they might not do what you think they should do, or they might not do what's best for them. That's one reason why, even though the math kind of says that you should be able to make more revenue, you have to really understand how people interact with randomness to exploit that. Yeah. So so kind of like what computer scientists have been doing is trying to understand. So kind of like previously, the theory really said that, hey, there could be this like infinite gap between what you can get with randomization and without. And that's kind of incomplete because that would suggest, I think, to an economist that it's really worth understanding how people interact with randomness if it's going to make you infinitely more revenue, right? Like, why would you not do that? So what we've been doing is kind of trying to understand how like really quantify better under what assumptions is it the case that actually you don't lose more than a constant factor, or there are other ways to kind of like gain the lost revenue and stuff like that. So that's yeah.
Something even more to the situation. And for instance, I mean, can you always model a randomized? Can you adjust the distributions on the buyer's valuations so as to sort of give you the same result as another distribution on their values but with randomization? I mean, what does randomization?
So
special and different properly getting the distributions correlated or not correct.
Yeah, okay, so think like there's kind of two things going on. One is the randomization in the distribution that the seller faces. So the seller, if the seller knew the values of whoever was walking in the door, like if I knew that you were willing to pay $3, I would say, pay me $3, and I would use a different price for everyone who walked in. So that's one source of randomness that makes a problem challenging for the seller. Now there's a different kind of randomness, which is once the buyer walks in, they can, the buyer has no randomness from this. Though the buyer knows their value when they walk in the door. It's not that the buyer walks in the door and says, I don't know what my value is, maybe it's 1, maybe it's 2, or something. The buyer walks in and says, I know my value is 1. And so if the seller doesn't use any randomness, then it's not a random procedure. There's no, does that make sense? There's no randomness for the buyer. If the seller chooses to use randomization, then they can kind of like, the word would be like either price discriminate better among the market, or they can like segregate the market better. So think like, right, like if you restrict yourself to deterministic options, then there's basically, you have like 3 parameters to try and segment a market into 3 groups of people. But if you're allowed to use randomization, now you basically have a continuum of parameters, and you could possibly segment the market infinitely well and get and does that make sense? You can almost treat everyone differently. Yeah, so I think more the randomization is for just to give you more options. It's not so much to play with randomization versus determinism. Yeah, that's a good question. Okay, so let me now get into our tools that I wanted to tell you about. So what I want to do is, let's see. So everything up here I want to keep for the rest of the talk, except that there's only 2 items and that there's only 1 buyer. So I want to look at multiple buyers and multiple items. But I still want the buyers to be additive. I still want all of the buyers' values to be drawn independently for each item and for each buyer. And the seller's goal is still going to be to maximize their expected revenue. I just need to be a little bit more formal about what it means to maximize revenue. So we're going to say that the seller wants to design what's called a truthful mechanism. Okay, and I'll use the following parameters to describe it. So they can come up with some variables. I'll call them pi ij of v and pi of v. And what do these mean? So currently think of the mechanism as just some object that takes as input, all the buyers show up, they say their values, and then the mechanism somehow allocates the items and charges prices. And I want to use these variables to denote the probability that, sorry, let me index these by I. Probability that bidder I wins item J over any randomness in the mechanism and any randomness in, I'll say, D minus I. Okay, so what this means is, so this is going to define for whatever mechanism you come up with. For any bidder and any item, you can define the following probability. The bidder shows up, when, there's one thing missing, when reporting VI. Okay, so you can look at bidder I shows up to the auction. As far as they know, they don't know anything about who else is going to show up. They just know that the values are going to be drawn from d minus I. Now this bidder is, there's lots of different bids they can make on the items. Let's say that they choose to report VI. Then, over the randomness of sampling everyone else's valuation from d minus I, maybe there's randomness in the mechanism, then the bidder will receive the item with some probability. That's what this is capturing. Okay, does that make sense? Okay, and then PI is just the expected payment of I over the same randomness. Okay, so I'm going to claim that these are kind of like the only variables that are relevant to define a mechanism. If you are so if you want to solve an optimization problem to find the revenue maximizing truthful mechanism. So let me just kind of maybe a little bit more clearly write what I mean. So I want to say that a mechanism is truthful. And the slightly more formal term for this would be Bayesian incentive compatible. So for all bidders and for all values that they might report, so let's parse this. This is just saying what is your value for if you report VI to the mechanism. This is the probability vector of items that you're going to get. This is just you evaluating your value times the probability that you get an item. Okay, so this is your expected value for participating, and this is the expected price you pay, and you want this to be at least as large as okay, and you want this to be at least as large as, well, there's nothing that forced you to say VI. You could have said VI prime instead. And had you said VI prime instead, you would have gotten a different allocation. Your values would still be the same, so you would evaluate the probabilities in the same way, and you would pay a different price. Okay, so you would like it. So this truthful means basically if you believe that the reasoning the bidders are going to do is they're going to come to the auction, they're going to say, well, I don't know what everyone else's values are. I know the population. I believe that everyone else is going to report their true values. Then it's in my interest to report my true values as well. And so the formal definition for this would be that it's like what's called a Bayes-Nash equilibrium for everyone to tell the truth. Okay, so this is what it means to be truthful. There are kind of some other conditions that I'll ask you to trust me that they're linear. So when we're trying to design one of these mechanisms, we also need to be mindful, like, for instance, clearly it's not feasible for me to propose a mechanism where, like, someone gets an item with probability 2 or something like this, right? Or for two different bidders and all of their types to both get every item with probability 1. So there are some constraints on what probability vectors can actually result from mechanisms that only give out one copy of the item every time. These are actually, it's an interesting problem to try and understand exactly what linear constraints tell you when this is feasible or not. I wasn't going to go over that today, but I will just write that there are linear conditions that guarantee this, and I'll just refer to these as being feasible. Okay, and I'll just put up, so kind of the buzzword for this is, so Border is an economist, and we call it like Border's theorem characterizes exactly what linear constraints tell you when a given probability vector can be matched by allocation rule or not.
The actual theorem is that all these constraints suffice, or
No, no, no. So the obvious constraints, so here's, okay, so since it came up, so let me just give you an example that it's not obvious. So I think the obvious constraints would just be that in expectation, every item should be allocated at most once. So that clearly has to be satisfied because, right, you can only allocate it once per instance, so the expectation better be less than 1. But let's say, here's an example. Let's say that let's say there's just one item, and bidder 1 has 2 possible types. I'll just call them A and B. Bidder 2 has 2 possible types, C and D. Let's say everything is uniform. And now let's say I want to claim that C gets the item with probability 1, D gets it with probability 0, B gets it with 0, and A gets it with 1. So let's parse. So I claim that the item is given out with probability, in expectation, the item is given out exactly once, right? So here, this is given out 1 times a half. This is a half plus 0 plus 0 plus a half. So in expectation, the item is only awarded once. However, you run into a problem when bidder 1's type is A and bidder 2's type is C. Now you're bound to give both of them the item, but you can't do this because you only have one item. So does that make sense? So this is why it's interesting to think about what additional constraints the probability vector needs to satisfy in order for there to exist a mechanism that only gives out one copy of the item on every single profile that also matches these. It wouldn't surprise me probably if you thought about it by yourself. You'd figure it out in not that long. But it's not obvious. It's a fun thing to think about. So, okay, let me swap these back again. Okay, so now I actually just kind of want to informally claim that subject to you believing me that this is feasible is a set of linear constraints. I claim that actually I've now shown that you can kind of write the search for the optimal mechanism as a linear program. Okay, so why is that? Well, these constraints, so the variables we're going to use are these pi variables and the p variables. The valuations are known. That's part of the input because you know the distribution. And these, if you believe me that they are linear constraints, all I've done is I've written a bunch of linear constraints on the board. Okay, and what's the objective? I should have written that before sending it up. It's you just want to maximize the sum overall I and the sum overall VI of the expected payment times, I'll use little fi. So what I mean by this is, I didn't say this before, it'll be easier just to think of everything as being finite support, just because I can write a linear program instead of a continuous linear program. It's not necessary for results, but it's cleaner. So I'll use little fi of vi just as shorthand for the probability that bidder i's full valuation vector is vi. And so what is this capturing? This is just saying, well, this is the expected revenue you get because this is the probability that bidder I has this valuation, and this is the expected payment that they make to you conditioned on having this valuation. Okay, so this is a linear program. It finds you the optimal mechanism. So it is, okay, so it depends. So the original paper proposed like 2 to the, I'll just write, so if there were t types per bidder, then there were t to the n constraints. So one way that I got into this is, so we do know that actually there's a set of only nt constraints that suffice. So this is if you're comfortable with like max flow min cut, then there is a max flow min cut proof that will give you t to the n directly. This one we had to work harder to get. It's again, it's not like mind-blowingly difficult, but it's not just you observe that max flow min cut holds and you can get, but this is easy to get. Okay, so now what I was gonna do, let me just make sure I have the right plan. Right, okay, so now kind of the focus of this talk, it turns out that the main barrier to kind of understanding the optimal mechanism is that it's really hard to prove non-trivial upper bounds on how good a mechanism can be. So one obvious upper bound on how good a mechanism can be is definitely you are not going to get more revenue than the expected value of the buyers for all the items, because there's no way that you're going to charge them more than their value in a truthful mechanism. But it turns out that this bound is just, it's way too loose. There are lots of distributions where the expected value is infinite, but the best revenue you can get is finite. So it's not the right bound to use. And this, so I'll just maybe assert, this is really kind of like the main bottleneck in progress for a while. And so what I'll show you is just that, maybe I'll also just state without argument that using kind of like full LP duality on this is a little bit of a mess, just because it just, I don't know, it's just a mess and did not lead to anything useful. But it turns out that kind of using LP duality, but in a little bit of a different way, led to useful bounds. So let me just quickly, just in case not everyone's familiar with what I mean, let me just write some quick duality preliminaries. So if I have a, so let's say I have some LP and I write it as max c dot x subject to x in p and ai dot x less than or equal to bi for all I, and I look at a different LP, which is max c dot x plus some I lambda I bi minus ai dot x. Okay, let me send to the side. So these are just two LPs. The first one is just an arbitrary LP, but I've decided to break up the constraints into two types. The second one, basically what I've done, if you already know Lagrangian multipliers, all I'm saying is that Lagrangian multipliers work. I've taken Lagrangian multipliers on these constraints, but I've left these in the feasibility. And there's an easy theorem that just says that if lambda I is greater than 0 for all I, then the value of LP2 is at least the value of LP1. Okay, so so this is actually super easy to see. If all of these are non-negative, and I take any feasible solution here, bi minus ai dot x is non-negative for all I. So I have something non-negative times something non-negative. Maybe it's 0, but otherwise it's positive. C dot x is the same, and this solution is feasible because x had to be in here, x had to be in p here, so it's still in p here. Okay, so any feasible solution here is definitely feasible here, and its value can only go up. Okay, so this just says this is one way to get upper bounds. And then the harder thing to prove, P is a polytope, sorry, yeah, is complementary slackness. Which just says that if whenever lambda I is, let me just write it. Okay, so if I have the following, lambda I is not 0 implies bi minus ai dot x equals 0, and x solves LP2, then both lambda and x are optimal. Okay, so what this means is just that if I happen to find a specific set of multipliers lambda, and I can find a primal solution x such that, so this is called the complementary slackness condition holds, and it happens to be an optimal solution for LP2, then I have actually found a true optimal primal to the original LP1, and these dual variables lambda are part of the optimal dual solution. Okay, so I wasn't going to prove this. Probably most of you have at least heard this, but that's, yeah, so that's complementary slackness. Okay, so with this, so basically all I'm going to do for the next little bit is I'm just going to take Lagrangian multipliers of the incentive constraints and not on the feasibility constraints. And I'm just going to rewrite stuff, and something interesting will happen. But that's it. Okay, so yeah, yeah. But it's not like a you know, wildly novel new thing to do. It's just something that had not been really fully explored before. Okay, so I want to use this notation, lambda I vi prime, and this is going to be the dual multiplier for okay, so when I write this, just I didn't want to write the whole thing out. So the IC constraint that says that vi does not prefer to say vi prime when it's bidder I, this lambda I is going to index the bidder, and then the vi and vi prime is going to be the real type and the type that we know they don't want to lie to. Okay? And all we're going to do, again, I said, so we're going to Lagrangify those and move them to the objective, and we just want to see what the new LP looks like, and we're going to do some rewriting. So I think I didn't write this down in my notes. So, okay. So let's see what happens. So the new objective is going to be, it's going to be long. So it's the sum overall I, the sum overall vi, and it's going to be, the original objective is still there. So this is pi of vi, fi of vi, plus, now we have to sum over every incentive compatibility constraint, I, vi, vi prime, lambda I, vi, vi prime, times vi times pi I vi minus vi dot pi I vi prime minus pi vi plus pi vi prime. Okay. And this is all such that pi is feasible. Okay, so this is not super interesting so far. Now what I want to do is try and just regroup what's written here in terms of each of these variables pi ij times a coefficient, and each of the variables pi times a coefficient, and see what we get. So I claim this is the same as sum over all I, sum over all vi. Okay, so let's parse what is the multiplier for pi of vi. So it definitely gets an fi of vi from this. That's easy to see. Okay, now it gets a minus for every vi prime. So there's a minus sum over all vi prime of lambda I of vi prime. And there's also a plus. It will show up here whenever it is the v prime and there's a different v. So it'll also be plus sum over all v prime lambda I of vi prime vi. Okay, so this was all I did was I just took the variable and I counted what are the coefficients that are going to be in front of it. And the other ones we're going to get, we can also separate out these. Let me do that by each j separately. So whoops. Okay, so what is it going to get? So it gets nothing from here. Sometimes it is the vi in this sum, in which case it gets a vij times this multiplier. So this is sum over all vi prime vij times lambda I of vi prime. And also sometimes it's going to be in this position. So there's also a sum over all vi prime when they're here. But this is going to be the vi prime j is going to go here. So this is vij prime times lambda I of vi prime vi. Okay, and this is again all such that pi is feasible. Okay, so this I think is, again, not super interesting yet, but everyone just follow. All I did was I took Lagrangian multipliers, I rewrote it so that I could group the p times their coefficient and the pi times the coefficient. So now what I want to Okay, so now what I want to observe is, okay, for this LP, there are actually no constraints on the prices, right? So now that we've Lagrangified all of the incentive constraints, there were no feasibility constraints that involve the prices. The only constrained variables are the pi's. So if any of the coefficients for any of the price variables is non-zero, then the value of this LP is infinite. Does that make sense? So if we have an unconstrained variable with a non-zero coefficient, then you can set it to either plus or minus infinity, and the value of the LP will be infinite. Okay, so what that means is that in any, whatever the optimal multipliers are, they definitely wind up giving a zero coefficient to every price variable. That has to be the case. So let's just write that as a condition. So this means that, so we'll say every, let's call that interesting dual has needs to have this equality satisfied. Okay, and now I just want to draw a quick picture. So what does this condition mean? You should think of it kind of like a flow conservation condition. So think of it as, right? So say I want, for every bidder, I want to draw a graph. This is just a mental exercise. It's not a, an algorithm or anything. I want to draw a graph, and I want to list all of the possible valuation functions. So let's say this is like VI1, VI2, VI3. So you should think of everything as getting flow in from some source. And the source is going to give everyone flow equal to their density. Okay, so you get flow equal to F of VI1, F of VI2, okay? And then the flow that you send from one type to another type is just equal to this lambda I VI1 to VI2. Okay, does this make sense? And now if, when you draw this picture, it is a valid flow, as in flow is conserved everywhere except the source, and, okay, so I was a little bit, okay, I'll write 0 here. So this constraint you should think of as, okay, I was a little bit sloppy. I hope this won't be unnecessarily confusing. In the feasibility conditions, you can also hard code that if your value is 0, then you get nothing and pay nothing. That's fine to hard code because there's no reason to do anything else on this valuation. And you don't need to write any incentive constraints involving this type. If you say that you don't value anything, this is like the non-participation option, basically. And so what you do is you do have constraints that say you don't want to lie and not participate, but you don't have constraints saying that this guy doesn't want to lie and say something else. So this acts as the sink, okay? So I hope that, okay, this is just like kind of like a technical aside, just because you would probably be confused if I told you that there was a source but no sink in this graph. This isn't really important. I'm just telling you there is a sink. And really what you care about is that this condition says that you need to conserve flow at all of the values.
But this condition, somehow the 0 is necessary because otherwise you can mandate participation.
Yes.
Make everyone pay
Yeah.
$1 million.
Yeah, that's right. So it's definitely necessary. And yeah, I guess without it, you would not have an interesting LP. You would not have an interesting solution. It's definitely necessary. I was just saying, I don't know. I was just saying it's not conceptually the interesting part. No. Okay, does this make sense so far? So now we understand what this condition is. So now that we understand this condition, actually, even if we didn't understand this condition, we could just do a substitution into the second line, because we have this constraint that says, well, I know that summing over all v prime of this must be equal to that. So let's go ahead and rewrite our new objective after this substitution. And so that's going to be sum over all j, sum over all I, sum over all vi, pi ij of vi times. Okay, so let's see what substitution we have. So note that here, this is sum over all vi prime, lambda I of vi to vi prime. Here, we have the same thing, and every time it appears, it's multiplied by vij. Okay, so we just get vij, so we can replace this up top with vij times this. Okay, so let's just write that. So vij times fi of vi. And now it's going to be plus sum over all vi prime. It is going to be vij minus vij prime of lambda I of vi prime vi. Okay, so again, all that went on here was we just observed if the dual is going to be interesting, if it's going to be not infinite, then you have to satisfy this flow condition. Plugging in the flow condition, we can rewrite the new objective because all of the price multipliers have to be zeroed out. And this is going to be just the pi ij times this after the substitution. Okay, so now I want to do one last rewriting, and then I'll claim that I've rewritten it in an interesting way. Okay, so I want to define, say, big phi ij of vi. I'll also use I might forget to write the superscript, but it depends on the dual solutions. I want this to be equal to, let's see, vij plus the sum over all vi prime, vij minus vij prime, lambda I vi prime vi all over fi of vi. Okay, so all this is a notation. Now I claim that this is also equal to sum over all ij vi, pi ij of vi times fi of vi times vij lambda of vi. Okay. And now, so I just want to stop for a second. So I want to claim this is interesting. Okay. So why is this? So if I told you that I wanted you to interpret this as being, so the terminology I would use would be a virtual value. Just think of it as it's like it's your value for getting item j, except it's not what's prescribed by vij. It's like I think of your vector vi, just think of it abstractly. It has nothing to do with values. But if this is your real valuation vector, I want to pretend that your value for item j is instead this. Okay? And now, so I'll call that virtual value. And now what is this objective? Well, it's summing over every bidder and every type. What is the probability that this type is present at the auction? Then it's saying conditioned on being present, what is the probability that you get item j? And when you get item j, this is your virtual value for item j. Okay, so all I'm claiming is that you can interpret this objective as what I would call virtual welfare. But the virtual values are defined, they depend on this lambda. Okay, and we saw that for every lambda, this is an interesting thing to try and study. Okay, so kind of, let's check the time. So in spirit, what this is saying is that one way to get upper bounds on revenue is to come up with interesting virtual, let me call this a virtual transformation. It takes as input a value of vectors, and it transforms it into a virtual valuation vector. Okay, so coming up with interesting transformations that preserve flow, that's one way, it's in some sense a complete way to get upper bounds on how good the revenue can be. Okay, so does that make sense? So that's the, the conceptual new thing, that this is a good way to think about upper bounds. So what I was going to do now, I can maybe pause quickly if there are any questions about parsing this. And then I was just going to instantiate this and show you some interesting flows that give interesting upper bounds. Some known result, mostly all known results though, because I think the newer stuff is messier. So I'll just keep going. That's good.
So the virtual values, are they interpretable?
What do you mean by that? Like,
So if this is a complete way, some virtual values realize the optimal revenue.
correct.
Are they special in some way?
So in the simplest settings, so in the single item setting, there is a nice interpretation for what those virtual values mean. Beyond that, I am not aware of a nice, so you're asking just like if I were to give you these virtual values, however they happen to be in the optimal solution, and not tell you anything about duality, could you look at it and say that's an interesting function? So for the single item case, the answer is yes. I can say something about that once I show you how to derive it. Except for the single item setting, I'm not aware of any nice interpretation of what they are.
It's kind of connected to pi. I mean, if pi times your fee is supposed to be representing price or some kind of revenue or
Yeah, so
hit from getting item J or something, whatever it is.
yes. So what you should do, so there's two other ways you can think. So this is from maybe a technical perspective, not an economic perspective. So from a technical perspective, what you're learning is first, if lambda I of vi prime, I mean, that's a dual multiplier for the incentive constraint from vi to vi prime. So if that constraint is non-zero, that means that that was a binding IC constraint. And if you didn't have it, you could make more revenue. Right? If that, and then kind of, I don't know that this is really fair to say quantitatively, but the larger that variable is, right, the more important that IC constraint is. The other thing is that what you observed is it kind of like if phi j of vi is big, this is like saying that you actually get a lot of revenue by giving vi item j, and that tells you that this is a good thing to do in the optimal mechanism. Kind of like what these virtual values are, they're kind of like an amortization. Let me just say why. So let's say that like I told you that I want to have a truthful mechanism and I want to give you the item when your value is 3. Then this costs me something because now I cannot charge someone whose value is 4. I can't charge them 4 to get the item because they could always lie and say their value was 3. And I also can't charge someone whose value is 5. I can't charge anyone more than 3 for the item anymore. Does that, let me say again. So like, if I want to give the item to someone whose value is 3 and I want to charge them 3. Why is that good? It's good because I make $3 from this person. Why is it bad? Because of the IC constraints, I can't charge anyone more than 3 to get the item anymore. Because it's already available. If you lied and said your value was 3, you would get it for 3. So these virtual values kind of capture that trade-off, and that you would look at the virtual value of 3, and it would exactly capture that you're getting some revenue by selling it to him, because and that is this part. This kind of captures this is the revenue that you're getting by selling it now, and this kind of captures this is the revenue that you're losing because it influences what you can possibly give to anyone else and still be truthful.
Sort of a blending of burden and opportunity.
Yeah.
Cost,
Yes.
opportunity pricing.
Yeah. So I think that's one way to look at it. Or I might say like it's an amortization of the cost. Yeah. So that's one way to look at it. So all that being said, this is kind of, I would say more like technical intuition. It's not like if I just were to give this, whatever the solution is, if I were to give it to someone and say, is this an interesting function? Most of the time, I'm not aware of them turning out to be interesting functions by themselves. Okay. Yeah. Sure. Yeah, that sounds good. And I guess during the break, would it bother anyone if I erased everything except for what's in the box, just to save time? Okay. Oh, yeah, that's reasonable.
Oh, you were talking about distribution.
So I'll just say with multiple bidders, the question is not so naive because you can think like from the seller's perspective, you can use the other bidder's values as randomness so like when there's only one bidder, that bidder shows up, they know their value. If the seller doesn't use randomization, there's no randomization. If there are two bidders and you don't know my value, the seller can kind of use my value as a random seed and technically be deterministic as a function of our two values. So there is, I believe, actually. So I've seen a paper, but I don't know if it was. I've seen a paper claiming that if everyone's distribution is continuous, then you can implement any randomized mechanism deterministically by cleverly using the other bids as source of randomness. Yeah, but that clearly in the single bidder case, there's no outside source.
Yeah, it's kind of like in physics, they have this issue of, is quantum mechanics really, is there fundamental randomness?
Mm.
You know, is it kind of built into the theory, or is it just because we don't happen to know some of the values?
Mm.
We don't know what the distribution is this or that. And if we knew it, then we would all be deterministic.
Yeah.
So I was,
there was a jump from the beginning of the talk. So, like the first example that you showed was framing things in some way, and then you gave the
Yeah. Okay. Yeah. Yeah. Sorry. So think of it in the following way.
Well, I think you went from one buyer to multiple buyers.
no, but
Yeah. So you're saying
because you assume
yeah.
values, right?
Yeah, so I went from thinking of mechanisms as a list of options and you choose whatever you want to thinking of mechanisms as you tell me your value and then I give you something. So what I didn't say was that this is an equivalent, they're really equivalent interpretations. So think of it as, let's go from one to the other. So say I want to think of mechanisms as you tell me your value and then I will give you something and I want it to be truthful. Then another way to think of that is I can just list the allocations that you would get and the price you would pay for all of the different values that you could report and offer that to you and say choose what you want. And then if the mechanism is truthful, you will choose the one that I tailored for you specifically. Does that make sense? And now if I want to go from one to the other, I can also say for any list, I can just define what I give you to be whatever maximizes your utility from this list. So for a single bidder, subject to having to do the mental exercise of jumping back and forth, for a single bidder, I think it's more natural to think of the list of options and you choose one, because that's just like, you know, we all go into stores and buy stuff, and so it feels simpler. For the many bidders, it's really more natural to think of the reporting of value when something happens. Yeah, does that make sense? Yeah, sorry. It's something that I think we take for granted, that it's easy to jump back and forth. Yeah. Start again. All right. So okay, so now. Okay, so with this in mind, I now want to just show you some interesting instantiations. So let's start. So even though I set this up to be a little general, let's start with just one item, but still many bidders.
This is your new objective.
Yes.
This is a rewritten objective.
Correct. So now we just want to come up with interesting lambdas. They have to form a flow. But subject to forming a flow, every single one gives us some upper bound on the revenue. And then with this thing that I wrote and erased was that if further we can find ones that happen to satisfy complementary slackness, then we can claim that the mechanism is optimal too. That's not going to be normally what we want to do. In the single item case, we can. So,
And one difference.
Yeah.
I mean, if your objective function is, you've kind of somehow decomposed or you've broken down or you've subdivided the objective function.
correct.
Right now, it depends upon these
Right.
groups or classes of the J.
Correct. So, okay, so let's parse this one more time. So this is, let me just swap the boards and write one more thing up here. So this is the objective function. What I erased and forgot to rewrite.
The objective function assuming that
Correct. Right. So I didn't write. Right. So this is for a fixed lambda. This is the objective function. We want to maximize and the constraints are that this pi has to be feasible. Right? So this means it's not like a separate bidder by bidder optimization, but actually, yeah. Let me talk about this a little bit more. So there's a joint optimization, right? That because this does depend on all the bidders in an interesting way, but I want to find over all the feasible allocations, find the one that optimizes this. So let's first just go through. Okay, so let's do something related to this before I start giving you interesting ones. So how should we parse this? Let's say when there is one bidder. Okay, so if there is one bidder, what does is feasible mean? So for one bidder, is feasible just means that all the probabilities are between 0 and 1. Okay, they're not interesting. So now, how do we optimize this? Subject to all pi ij's are in 0, 1. That's easy. It's just if this is positive, I want to set pi ij to be 1. If this is negative, I want to set pi ij to be 0. If this is 0, then maybe I have to set it strictly between 0 and 1 to satisfy complementary slackness for the optimal mechanism. So this is, let me just as an aside, this is where randomness comes from. Randomization comes from because maybe this is 0, and in order to satisfy complementary slackness, you need to be clever here. Okay? But definitely, whenever this is positive, this better be 1. Whenever this is negative, this better be 0. Okay. Now let's parse what happens in the multi-bidder case. So let's go back to, without worrying about the, the formal definition of feasible, what was the semantic meaning? The semantic meaning was that there exists an allocation rule that awards the item at most once on every profile and matches these probabilities. So I claim that the right way to reason about that is that you say, well, okay, what should I do on any given profile when everyone has shown up and reported their bids? Well, what you should do is you should look at everyone's virtual value for each item, and you should give the item to the person with the highest virtual value, because you're trying to maximize this virtual welfare over all feasible allocations. And the point is that feasibility decomposes very nicely into an instance-by-instance constraint, but truthfulness didn't. So that's why it was nice to keep this one but get rid of the incentive constraints. Does that make sense? So one more time, the incentive constraints really depend. They're not like you can just look at what are the values of the people who are right here and decide what to do for them in isolation without worrying about the incentives that they cause for people who aren't here right now. But for feasibility, you can, right? For feasibility, for the people who are here right now, you're allowed to give one copy of each item, and that's it. It doesn't matter what you do on people who aren't here. So when you do this optimization, since these are your only constraints, you can really do it instance by instance and just say, when people show up and they report these bids, I want to give item J to whoever has the highest virtual value, because that contributes the most to the objective. Okay, so does that make sense? So that's another way why this is nicer to work with. So when you think of searching for a good dual solution, you're searching for a lambda such that, when you generate these virtual values and you optimize over all feasible allocation rules, that number is as small as possible. Okay, so that I think is intuitive. Again, like if you were actually searching for a good lambda, that's how you should think of the search.
So
Yeah.
Are lambdas, is there a way to think about the best dual lambdas? Because the extent to which you want to pretend to be someone else, like if you're a 5
Yeah.
and the 3s are getting
Yeah.
items, for sure you want to
Yeah.
pretend to be a 3 completely, but some other cases.
Yeah, no, that's right. So let me show you now the example for a single item, and you'll see why it makes sense as the right dual. So let me propose a flow. So remember we said we had this big source, and for a single item, so remember we said the flow is separable across bidders. So let me just write what it would look like for one bidder. So let's say there's this V max. Let me write V bar. So this is the highest value. Let me also, just for simplicity, write everything as integers. It's not necessary. It's just going to make the notation cleaner. Let me do V bar minus 2. And then all the way down here, we have 1 and 0. Okay, and we know that the source sends in Fi of V bar to here, Fi of V bar minus 1, Fi of V bar minus 2, and so on. Okay, and the flow I want to propose is just send everything straight down. Okay, so intuitively what this is suggesting is it's suggesting that, well, the important incentive constraints are the ones that say you don't want to lie by underreporting your value by 1, or underreporting your value as minimally as possible. So let's see what that will look like. So here, you get flow in Fi of V bar, so your flow out has to be Fi of V bar. Now, you get flow in Fi of V bar minus 1, Fi of V bar. So you send out, I'm going to cheat ahead and write this as 1 minus big Fi of V bar minus 1, and so on. And then the flow, let me say 1 minus 2, and then the flow into 1. Okay, so you see what's going to happen, right? It's going to sum the densities of everyone who is strictly above you. That is the flow that you are going to get in. Okay, so I'm using big F to mean you and all of the densities below you. Okay, so 1 minus big F is all of the densities strictly above you. Okay, so then here you'll get 1 minus big Fi of 1. Okay, so this is definitely a valid flow. Let's now plug into this equation and see what virtual values we get. Okay, so it's going to be equal to So I'll just write v, because you only have one number that defines your value. It's going to be equal to v, because the v is there. And, okay, so now you get flow. So again, so this is summing over all other types. This is the flow in that you get, vi prime to u. So you only get flow in from one other type. It's one above you. So v minus v prime is minus 1. And it's divided by your density. Okay, so it's going to be equal to, okay, I'll write it in the same notation. So it's going to be minus 1 times the flow in. The flow in is 1 minus big Fi of v. And divided by your density. Okay? So let me just, okay, I'll leave it like this. Okay, so this is what you would get out of it. Okay, so I'll just assert, I don't know if anyone's, like familiar with this stuff outside of this talk. So this formula is specifically referred to as like Myerson's virtual valuation function. Okay, so the fact that this is interesting was discovered in like an 81 paper of Myerson. He won the Nobel Prize, I think, in 2000. I don't remember actually. In definitely the last 10 years or so. And basically his paper is like what started this whole field of Bayesian mechanism design. And so he observed kind of like the special case of this for the single item setting, and he observed first that this is interesting, that this is a specifically interesting virtual valuation function. Let me assert without proof, just to answer Mark's question from earlier, this specific virtual valuation function captures the following intuitive idea, is that if currently you are setting price v, how much to just this bidder, how much revenue would you get? If I increase it by dv, a teeny bit, so if I increase the price barely, what is the change in revenue that I get? Okay, so I can write this function, so the revenue I get is equal to 1 minus big F of v times v. And this is, okay, it's not the derivative when it's basically the derivative of this function. There's a change of variables I don't want to get into, but basically it's the derivative of that function. So this captures kind of, if I were to increase the price, how much would my revenue go up, would it go down? If so, what is the rate of change? Okay, so now with this in mind, let's revisit complementary slackness and say, when is this especially interesting? So if it happens to be the case that for every bidder, this is a monotone non-decreasing function. Okay, so if it's the case that if phi I is non-decreasing for all I, then I claim that there is a simple mechanism that satisfies complementary slackness as a function of v, yeah. Only in v, yeah. So for all I, it's non-decreasing in v, yeah. So here's the mechanism I claim. So we already talked. So we already talked over here that obviously the mechanism has to be give the item to the bidder with the highest virtual value. If these virtual values happen to be monotone non-decreasing, this means that when your value is higher, you are only more likely to get the item. So the resulting allocation rule from the only possible optimal mechanism will happen to be what's called monotone. So it'll give you the item more often as your value gets higher. And it's known, maybe I won't give the proof, but it's known and it's not hard to prove that if you have a monotone allocation rule, there always exist prices to make that truthful. And it's an if and only if. If the allocation rule is not monotone, there are no prices you can charge to make it truthful. Okay? So what this means, and he actually named this condition, so now we call it regular. Okay? So if it's the case that every distribution is regular, so that these specific virtual values are monotone non-decreasing, then we know exactly what the optimal mechanism is. So the allocation rule will be the following. On every profile, you give the item to whoever has the highest virtual value, and then after the fact, you just charge the right prices to make sure that it's truthful. But I claim the interesting thing is understanding the allocation rule, not so much understanding the price rule. Okay, so does this make sense? So this is one way that you could prove Myerson's result. If it's not regular, yeah. So let me now describe a. Okay, so let me observe. I asserted that this function better be monotone non-decreasing. Otherwise, there's no way for you to get a truthful mechanism out of it. So let me describe now a procedure to basically, I would call it iron. He used the term ironing to kind of like iron out any non-monotonicity. Okay, so let's say that there is some, let's say it's here, that v bar minus 1 and v bar minus 2. Let's say that v bar, the virtual value here, is less than the virtual value here. So I claim that if I add a cycle between these two types, then it will average them close. It'll preserve the average, but it'll make them closer together. Okay, so let's just parse y. So let's say that I add a cycle, and let's say that it has weight x. Let's go to this formula and see how does that change everything. So the virtual value of, we'll look at v bar minus 1 first. It now has more flow going in, and it's coming from someone where this is 1. So v bar minus 1 minus v bar minus 2 is 1. The extra flow going in is x, so you get an additional x over your density to your virtual value. For v bar minus 2, it's the same thing. This goes up by x, but this is minus 1. So your virtual value for v bar minus 2 goes down by x over its density. Okay, so the observation is that this preserves the average among them, because one is going up by x over the density, one is going down by x over the density, and we can increase the one of v bar minus 1 and decrease the one of v bar minus 2. So if there's a non-monotonicity, this operation will preserve the average but fix it. And then the claim becomes, well, so if this doesn't work, you can always iron out non-monotonicities. So Myerson actually gave a closed form for how you can do the ironing kind of like in one shot without thinking of it like an algorithm. And that will give you what he called ironed virtual values. So ironed virtual values always exist, and the optimal mechanism always gives the item to the bidder with the highest ironed virtual value. Okay? One comment is that in order to, so now let's just observe that we have a bunch of extra non-zero lambdas here. So in order to satisfy complementary slackness with the optimal mechanism, with the dual, we have some extra constraints. So in particular, we have edges going both ways between these two types. And I claim that the only way that a mechanism is going to have both of these constraints be tight. So remember, this is saying that v bar minus 1 is indifferent between what they get and what v bar minus 2 gets. And v bar minus 2 is indifferent between what they get and what v bar minus 1 gets. And I claim that for both of those to be true, they have to get the same allocation and pay the same price. Okay? So what this means is that in order to satisfy complementary slackness in the optimal mechanism, in addition to always giving the item to the bidder with the highest virtual value, you can't just break ties arbitrarily. You have to break ties carefully and consistently. So if you would give the item to the bidder with value v bar minus 1, you have to give it to the bidder with value v bar minus 2 also. You can't decide, does that make sense? Like you can't decide to break ties inconsistently and still satisfy complementary slackness.
That ironing process isn't that sort of doesn't it depend upon which you sort of iron out first? How you do it?
So it,
Ties or things are going to end up being tied.
yeah, so it happens to not. I think that's it's not something I want to prove maybe. Let me say kind of how the proof would go. So let's start by trying to figure out, is the bar going, let's look at what so I'll call it an ironed interval, is a set of consecutive set of values that have all been cycled together. So let's look at what is the ironed interval containing v bar going to look like. So I claim that it's going to be equal to, go from here all the way down, and look at the average virtual value on each of these intervals. So look at the average, his virtual value, the average virtual value of the top two, the average virtual value of the top three, and so on. And I claim for sure his ironed interval is going to be equal to wherever the highest average is. Okay, and the reason I'm claiming that is because assume for contradiction, say that the ironed interval was shorter, then because the average goes up as you go further down, there's still a non-monotonicity left, so something is wrong, right? And you know, same thing if the ironed interval went longer, I mean, it means we did some unnecessary ironing that you can undo. So maybe let me describe, you can also, if you have a strict monotonicity here, then you can undo the ironing and again bring them closer together. Does that make sense? That's a little hand wavy, but the claim is that it does happen to be unique, what you get. Okay, so now, let me see how much time is left. Oh, it's still a lot of time. Okay, so let me state, okay, so this is Myerson's theorem. There's another really seminal result called, you know, due to, so there are also economists Bülow and Klemperer. Let me state, so I can state that result and I can prove it. Also, the proof is super short once you have this terminology too. So their result shows the following. So this is Bülow and Klemperer. Is it, okay, so if, let's say you have n IID bidders and one item, then I'll write the following. So opt, oh sorry, and so say opt of n, how should I write this? Okay. Okay, let me, my notation, probably not a perfect choice, but let me parse this. So if f is a regular distribution, by n comma f, I mean that there are n bidders. All of their values are drawn independently from the distribution f. Opt means the optimal mechanism. Second price just means all I'm doing is I'm just soliciting bids and I give it to the highest bidder, they pay the second price. What's the revenue of that mechanism? Okay, so the claim is that, okay, second price mechanism is, for the most part, never optimal. But what this is claiming is that if you can just recruit one extra bidder from the same population to show up, then this is better than you don't need to know anything about F to run this also, right? You can run a second price auction without knowing the market. Just saying it's better to just get one extra person to show up than it is to learn the market and run the optimal mechanism with one less bidder. It also means that in a large market, you get like a 1 minus 1 over n approximation with just a second price auction, assuming that it's regular. I have no idea, yeah. so let me parse, so 1 second comment is, so there's second price, and then there's second price with reserve. So this is saying you don't even need to use a reserve. So on eBay, most buyers do sell using a reserve. But what this is saying is that if, you know, it's saying that you don't need to do that. eBay is also a little bit different because you're not trying to maximize your revenue, you're trying to maximize like your profit. So certainly you should at least set a reserve equal to, your own value for the item. Yes, yeah. That's so that's also true. Yeah.
Can you explain what second price is again?
Yes. So it's just you take all the bids, the highest bidder wins. They pay the second price, and this is claiming what's the expected revenue of this. Okay. So, and the proof is actually just 2 lines. Yes. Yeah. Sorry. Yeah. So here's. Okay, so observation 1 is that, let's call this opt star of n plus 1 f is at least opt n f. Okay, so what is opt star? I'll just say it out loud. It's, you can use any mechanism you want, but you have to always give the item to someone. Okay, so with opt, sometimes maybe you will say, if everyone's value is too low, I would prefer not to sell it because I can charge other people in the population more. Opt star just says you have to give the item to someone. Okay, so why is this obvious? Because take any mechanism that you would use for opt, and whenever it doesn't award the item, just give it for free to the n plus first bidder. And you get exactly the same revenue as before, but maybe there's something better you can do. Okay, and now the second observation is just if f is regular, then opt star of n plus 1f equals second price. Okay, so let's parse this. So we know that virtual values are always monotone. So that means that the optimal mechanism will always give. So sorry, we know the virtual values are monotone, and because the bidders are IID, they have the same virtual transformations. Okay, so this means that definitely the highest bidder has the highest virtual value. So So what this means is that giving the item to the highest bidder definitely maximizes virtual welfare. Okay, now the question is just, does it also satisfy complementary slackness? And if f is regular and you didn't have to worry about this ironing, then you can tie break among different virtual values however you want. So the answer is yes, it does satisfy complementary slackness. So if f is regular, then does this make sense? So if f is regular, you are free to always give it to the highest value. Why is that? Again, because it definitely has the highest virtual value, and you have no interesting tie-breaking constraints. Okay, the reason you need regularity is because if you have ironed intervals, it might say that you're not allowed to tie break however you want. Let me just give an example of this. So here's one not regular distribution. Is let's just say that the distribution is uniform between even just like 0, 1 will work. Okay, sorry, that's a bad example. Let's say that the distribution is 1 with probability 1/2, and it's like 2, sorry, I'm just being lazy. So like 1 with probability 1/4, 2 with probability 1/4, and like 100 with probability 1/2. Okay, so now let's just think. So what would be bad about only doing second price? So what would be bad is that if you look at the 2 bidders, and let's say that the bids are 100 and 2. Now, second price auction will charge price 2 here, but maybe if you just kind of do some quick reasoning, you'll see that really it's better to charge price 100 even though it means that if instead his bid was 2, you're not going to sell the item. Okay, does that kind of make sense? So the point is that you can't just always give it to the highest bidder. In this case, it's actually better for you to just randomly award the item. Does that kind of make
That's very non-regular.
Yes, it's extremely, yeah. So this is extremely non-regular. So like this guy's virtual value is going to be extremely negative, because basically what's going to happen is that you're going to realize that I really don't want to set price 2 because it's way better to set price 100. Does this kind of make sense? Like if you, yeah, anyway, so that's the point, that you get into these interesting things where like you really have to treat 2 different values the same in order to be optimal. And again, that shouldn't be surprising because it comes from complementary slackness, but just chasing it all the way through is sometimes, I think, a little bit surprising to see the consequences. Okay, so that means that when f is irregular, then sometimes the optimal mechanism really does need to carefully break ties, and you are not allowed to just always give the item to the highest bidder. Sometimes you have to, randomly give the item among many of the almost high bidders, or anyway, yeah, sorry, does this make sense? But subject to regularity, this proof is like super clean, and that's it. So these are 2 nice results that you can prove. So they were known before this framework, but I think, my opinion, I think this is kind of like the right way to prove them. And that's because now this same approach also can be used to do more interesting things. So maybe let me show you one more result, and then that'll be it. So let me erase this, actually.
So I find that kind of concerning. Because it means that if you approach some person who is actually doing an auction and try to convince them to hire some mathematician to figure out their best way of doing things, that essentially they're better off just spending the money on advertising and getting.
Yes, so that is how economists would interpret it, yeah. So I think what that means is that if mathematicians are going to make their money in auction design, it has to be in multi-item settings. It's not going to be single-item settings, because single-item settings are really well understood. Fortunately, that's everyone is selling multiple things, so there's still jobs. So okay, so maybe also before I get started, let me just say that like what I think is useful about this framework is that even though it took us 90 minutes, I guess, to build up the machinery, now that we have the machinery, I'm fairly confident that I can prove like a really nice result in like 10 minutes, just since we have I'm saying this is most of the work. So what I want to do now is go back to the single bidder and the multi-item case. Okay, and what I want to do is define a flow. And the flow I want to define is the following. It's going to be easier to do in a picture. Okay, so this is 1, 1, 2, 1, 3, 1, 3, 2. Okay, and what I want to do is break this. So this is what the flow would look like for 2 items. I want to break this region based on which item you value more, and we'll break ties so that the vertical item is valued more. And now the flow I want to define is just everything you get in, you send it towards this line, and if you would have to send it over the line, you just send everything to the sink. Okay, so just okay, so does this make sense? So this is right. It's definitely a flow. I haven't said what values go on these edges, but I'm just saying whatever you get in, send it along these paths. Okay. Now let's see what goes along these edges. So this guy is going to get input equal to his density. Remember that this is your entire density, not just your density for one item. And it's going to go in and it's going to go through this process. So I claim that the total amount of flow that goes this way is going to be equal to, I think at this point it's better to just write the formula. So I claim that lambda I of V plus so this is going to be if J is the item where the flow got sent along, then I claim that the flow that's being sent is equal to 1 minus Fij of Vij times the product over all J prime not equal to J of little f, and that's it. Okay, so let's parse why am I claiming this is true. So this guy, if we were to extend this picture back, this guy is only getting flow in, like right in this region, all of the flow is going from right to left, and it's staying within the same vertical spot, right? So that means that within this vertical spot, all of these densities are being multiplied by this product. Subject to being multiplied by this product, it's the exact same reasoning as before when we computed the flow for the single item case, right? So it's just the rightmost guy sends in Fij of Vij bar times this product, and then you add your density times this product and same thing. Does that make sense? So this is going to be the flow that goes in. Now let's parse what do the virtual values look like with this flow. So in this formula, right, so we have Vij, let's just write it again. So we have Vij plus, you only get flow from one person. Let's first look at J prime. So for some J prime not equal to J, what's it going to be? So it's Vij prime. But now Vij prime minus Vij prime prime, they're the same, right? Because when I send flow from right to left, 4 is larger than 3, but these ones are the same, right? So for every value except for the axis that you're moving along is the same in the source and the destination. So this is going to be 0, and this term is just going to be completely killed. Okay, so does this make sense? So except for the value along the axis we're moving, your virtual value is just your value. In the axis that we're moving, well, now let's just write through the math. So it's Vij plus, this difference is going to be minus 1. We said the flow that you get in is this. And the division is your full density. So it's the whole product. So it's Fij of Vij times this. Okay? And now we can just observe, okay, the products cancel. And now we're left with exactly the same formula that we had in the single item case. Okay, so what this means is that with this flow, your virtual value for all of your non-favorite items is equal to your value, and your virtual value for your favorite item is your Myerson virtual value. Okay? So this is going to be our upper bound. And now so this is the upper bound we're going to use, and now I think it will just take like 5 minutes to show that there are interesting mechanisms that can target these upper bounds. And actually, this is the last virtual values we're going to define, so I'm going to erase this formula also. Okay, so now let's write, so what our benchmark is we have the sum over all items. We have the sum over all, so we don't need, I'm going to drop the subscript of I because there's only one bidder. So the sum over I is the sum over all values. We have fj of vj times, let's write it the longer way. So the sum over all valuation vectors. Okay. Sum over all items. Now we have vj times the indicator that there exists a j prime. Vj prime is greater than Vj, plus, I'll use, so I'll just use this notation little phi to denote specifically Myerson's virtual value, plus little phi j of Vj times the indicator that there does not exist a j prime. And all of this is times the probability. Okay, right, so okay, sorry. So let's parse what's going on here. So we have the virtual valuation function. We said the allocation rule that matches that virtual valuation function is the following. If it's positive, set the allocation to 1. If it's negative, set the allocation to 0. The values are always positive, so the allocation is always going to be set to 1. Virtual values might be negative, so we'll set it to 0. If the virtual valuation happens to be negative, all I claim is that taking a max with 0 here accomplishes that. Okay? So now, I want to do the following. I just want to decompose this and target the two terms separately. So let's look at this one first. This one is really easy. So let's just look at, again, so sum over all v, f of v times the sum over all j, let me even, okay. Okay, so this is what we have. I claim this is actually upper bounded by sum over all j, sum over all vj, okay. So all I'm claiming, basically in going from the left to the right, all I've done is I've upper bounded this indicator by 1. Okay? And now the observation you're supposed to make is that this is truly separable across items. Right? So I just have, for every j, there is no mention of any items besides j in here. This is just saying that this whole term is less than the Myerson virtual value that you can get by selling item j by itself. Okay, so what you're supposed to, okay, so I'm not going to finish everything I thought, but what you're supposed to conclude from this is that this is less than or equal to, I'll use this notation, S rev to denote this. This means if you actually just sold every item separately, how much revenue would you get? Okay, so maybe it's not 100% obvious, but I claim with a little bit of thinking, you would see that this is exactly this. Okay, and then what, you know, I thought I would have time to do, but I don't, is you can look at this term, and you can show that this term, the top one, so just to parse again, this is your value for all of your non-favorite items, that you can upper bound this by 3 S rev plus 2 B rev. Let me say what these are. So S rev is the same thing I said. You sell every item separately. B rev is you just post a single price on the entire bundle together and say take it or leave it. So,
Can it be so much?
sorry?
Can it be this high?
Can it actually be 6, you mean? So I don't know any examples yet. So what you would conclude from this is that, that the opt for this case is upper bounded by 4 S rev plus 2 B rev. And in particular, this says that either selling separately or selling everything as a bundle gets you a 6 approximation. Okay? We actually know that you cannot get a constant factor approximation just by selling separately. There are examples where the gap is logarithmic, and there are examples where the gap is linear for bundling together. Okay? But if you use both, then you can cover it with 6. And okay, this analysis is pretty simple, but I guess it would take me longer than I thought it would, so I won't do it. Does this make sense? And but it's just like elementary probability at this point. But the point is that all of the interesting work was in getting the upper bound, and that the upper bound was kind of through this principled duality way. And I was going to state, maybe I won't state formally, just so since then, there's been like a ton of new results kind of designing simple, approximately optimal mechanisms for even like buyers with combinatorial valuations, right? So even if they're not additive, but they have submodular valuations for items, and now we have constant factor approximations for this. And again, this approach is what gives you the upper bound. We now have the right generalization of the Bülow-Klemperer result to multiple items. And here, it's not enough to just add one extra bidder, but we have an idea of how many extra bidders you need to recruit in order to cover the revenue of running the optimal mechanism in the original setting. Yeah, there's a lot of other kind of twists on these problems that people are studying too, and the selling point is just supposed to be that this principal duality way of thinking about it, I think, is like the right approach. So, okay, let me stop there. Yeah.